Alrighty, morning everybody. Welcome back to Calc 1. Plan for today is we're going to finish off Standard 11 and then move into Standard 12, which we will be doing the same thing but with transcendental functions. So how to take integrals of trig functions, exponential, and not log functions, that comes much later, but integrals that involve log functions and so on. As far as office hours go, I've got my usual office hours the next few days, today and Wednesday at 11 and 2, tomorrow at 11 and at 1. As far as homework goes, oops, I forgot something. I posted a new homework 15, which will be due Monday. And also, we're going to have a quiz Wednesday over Standard 11. Heads up, no class this Friday. It's fall break. So enjoy it while you can. That's why usually I assign the homework to be due 2 class days later. That's why the homework I assigned for today isn't due for another week. That is Monday next week, by the way, if that's clear. It's because Friday, day off. I don't want to assign something to be due over fall break. That feels rude. Any questions or comments before we get started for today? I'm still a little bit behind on grading retests. Plan on catching back up on retests probably tomorrow. And once I do, I will post updated scores on Canvas with everyone's mastery totals. Alrighty, so a statistics student accelerated before crossing every intersection in a dangerous sort of way. The passenger finally asked, "Why do you go so fast through intersections? Isn't that unsafe?" Student replied, "Well, statistically speaking, you're far more likely to have an accident at an intersection than anywhere else. So it only makes sense to just spend less time there."
Never thought about it like that.
Say what?
Never thought about it like that.
Good. Don't think of it like that again. Okay. So if you recall, last class we talked about integration of functions, where we said that the integral of a function is a set of all antiderivatives of the function. And big F of x is any antiderivative of little f of x. In other words, a function, big F of x is a function that if you were to differentiate, you would get little f of x. And the fact that we have this plus c at the end of our integral, why do we need a plus c? Josh?
Because there's any constant can fit there, so it just kind of takes care of that.
Yeah, basically because because adding a constant term to the end of your function won't affect the derivative at all. If big F of x has a derivative of little f of x, then big F of x plus any constant will still have a derivative of little f of x. Because the derivative of the constant term is just 0, as we see. And we talked about some rules like reverse power rule. Which the way it worked is if we want to integrate a power function, we're going to get, we add 1 to our exponent and then divide by our new exponent. And that only worked if n is not -1. Because if n is -1, meaning we're integrating 1 over x, then we would be dividing by 0 if we use this formula, and that would be sad. So what I thought we could do, start class off today, is in the, where's my notes? Here they are. is I want to give you all a few minutes to look at some of the integrals in the back 2 pages of the packet, where I give you several functions, starting with x cubed plus 5x plus 4, and continuing on to the next page, that I would like to talk about how to integrate. And so what I'd like for you all to do is to go ahead and take a few minutes and take a look at these 6 integrals with your neighbors and see if see what you can make of them. And then after a few minutes, we'll come back together as a class and talk about what we found. Is it?
This thing.
I don't have any extras printed off. If you want to go log on to Canvas, I do have the packet posted there. And if you remind me, I'll email you after class with a copy if you like. I'll go ahead and write up the integrals on the board though.
Nice.
Actually had it.
I don't know. Yeah, I think I did this one.
No, there.
How did you do the 3 squares of x?
Well,
Oh, so you did 1/2. I just don't understand how you get the combination.
So you pull the 3.5 down. So it's gonna be 3. So you do the 2, the 2's cancel out, so then you get 3. Yeah. It's like whenever it's a power rule, so whenever you put the n, divide by n plus 1, you don't have to actually write it out because then you cancel out.
As always, you are encouraged to talk to your neighbors or to flag me down if you have any questions about something.
So did you get the third one on the first page?
No.
You'd have to use the
I don't know what that
average quotient.
Yeah, but he said like, could you bring it up top and factor it in? Can you do that in the integral?
Nah, that's too much
That's
work.
still,
I'm very confused.
That's a lot of work. And that would be a lot harder.
Yeah, but divided by -1 is just.
That's the only way to do that.
Incorrect,
There's no,
but very close.
because it'd be x to the
You're right,
0.
Because
divided by 0. You're right, you can't use reverse power rule on that. It doesn't actually come out to log of x, but you're very close. We'll talk about why today or Wednesday.
1/9.
Yeah, natural log or extra log x, I can't remember.
have you done the rule right here?
Oh, yeah.
That would be a good way to rewrite
It'd
that.
be,
I'm crazy.
you have to subtract or add.
Add 1, divided by.
You have to add
Can't
one.
do algebra.
Sounds good so far.
Because this is the bottom, so it's
Some
like
pretty
negative.
predictable signs,
Yeah.
but
Oh.
You have to
before you
add
actually
that.
integrate, but yeah, it looks like I'm
You
on,
minus-
The next one's just.
I'm on board.
Do I have to?
It'd be 3, so that
So,
would
like,
be plus 1.
This is one-
right now it's
It'd be nice to, it's not necessary.
To be
I will say that on your last.
3 to
The
the
bottom one I do not do.
I'll show you later. I'm not very good at explaining, but I'm just gonna do it.
So then
Indeed, yeah,
over
like I said, it's an easy thing to forget.
You can't
it's
define.
bad.
It's bad.
It's bad.
That's why I said.
It's
It's
natural.
bad.
I know it's long.
It's a no for me, dog.
I just don't remember.
I'll give you,
Because you can't write it.
I'll give you
This
an,
one?
it's an absolute value sign you're missing.
Oh.
I was close. I was closer the other day.
I was gonna say, like I said, answer's very close. For technical reasons, it's not just mathematical.
I don't either.
And
I think we don't shit.
so you have to
How
use a
much
backwards
more?
quotient.
Yes, they do.
Wouldn't you? But there's, I don't want to do that, so
I don't know how to do that, how backwards quotient goes.
it'd be tough. But I don't know.
Is there another way you can rewrite this original expression in a way that would make it easier to integrate?
I don't know.
4t to the negative 2 or something.
Yeah, but that you can't do that.
Say what, Jack?
Like maybe put in like the product rule. Could you factor it in or no?
Well,
Because then if you
Could you do?
like
is there any way we can
highlights
split
everything.
this one up into, everybody's looking at me. Is there any way we can split this one up into 3 terms?
Yeah.
Oh wait.
Oh yeah, you could do the 4 over 2, or 2 over 4, 3 over 4, and then 1 over 4, and integrate it out that way.
I think that's the best way to handle that one.
I'll do it.
He's killing us.
I know, how devilish of me.
That's an equal half.
Yeah.
Plus 3/4 t.
Bless you.
Thank you.
Well, let me put it this way. If we take the derivative of the product of two things, is the derivative of the product just the product of the individual derivatives? We'd have to do product roll, so. Unfortunately, I don't think we'll be able to integrate quite so nicely. So instead, can I see instead of this step, and then I think you can get something where you don't necessarily need to do some sort of reverse product.
Thank you.
Go ahead and take another minute or so, and then we'll come back together as a class to talk about a couple of these. Alrighty, let's come back together as a class to take a look at a couple of these. So let's put it to a vote. We'll do, again, the two problems from this that get the most votes, and you're free to vote for multiple ones if you like. Who would like to see this first one? This second one? Third one? Fourth one? Fifth one? Sixth one? All right, so we have two winners. Let's take a look at this one. We have an integral. Okay, that t's going to throw me off. Integral of 2t squared plus 3t cubed plus 1 all over 4t squared. So first of all, is it okay to take this and write it as the integral of the numerator divided by the integral of the denominator? Josh?
Yes,
Why?
because with the one rule we learned on Friday, with doing that, you can like break it up to 2t squared over 4t squared dt plus 3t cubed over 4t squared dt, and do that across the whole way, and then you can solve it that way.
Okay, so I asked you, Josh, if we could do it, if we could break it up into two separate integrals, and then you said yes. Here's a completely another idea.
Oh, I thought those meant the same thing.
Oh, gotcha. No. Oh, we'll get to your idea. We'll get to that in just a second.
So that doesn't work.
Why doesn't it work? I agree, this doesn't work. But specifically, if we could take the derivative of, basically, if we could integrate by taking integral of the top divided by integral of the bottom, that would imply that we could then differentiate whatever this came out to by taking the derivative of the numerator divided by the derivative of the denominator. And what rule tells us we can't differentiate a fraction by just taking derivative of top divided by derivative of bottom? Yeah. Unfortunately, we can't do this. This way does not work because it violates the quotient rule. So, in general, just like with products and quotients, you can't just differentiate like a product by taking derivative of first term times derivative of second. You can't differentiate a quotient by taking derivative of top divided by derivative of bottom. The same thing is going to hold true for integrals for pretty much the same reasons. Towards the end of the semester, we're going to look at some advanced integration techniques for how you could integrate, how to do the product rule backwards, so to speak. But there kind of isn't really a good way to do the quotient rule backwards, so we would be out of luck trying to integrate a quotient. Unless, Josh, what's your idea?
You just break it up into 3 separate parts.
Ooh, okay. Take this and break it up into 3 separate fractions?
Yes.
I'm on board with that. That's something you're allowed to do because we're not integrating anything. We're just rewriting this initial expression here. So we could write this as the integral of 2t squared over 4t squared plus 3t cubed over 4t squared plus 1 over 4t squared. I don't think we've quite gotten around the issue yet where we still have these fractional expressions involving t's that we need to integrate. So what else could we do with this expression that will put it in a form that's easier for us to just simply integrate? Zach?
You could simplify it so the t squareds in the first one would cancel out, so it'd be 1/2 plus 3t, well 3/4 t. And then you can't simplify one, so it's just saying.
Like that?
Oh, you did that, hours.
Oh yeah,
Yeah,
I'm gonna write t to the negative 2 just so in the next step it's easier to use reverse power rule on it. But yeah, I like it. So in other words, as what Zach has proposed is that if we simplify each of these first two fractions to 1/2 and 3/4 t respectively, we're actually going to end up with terms that are much easier to integrate. And so now, I think we can actually go through and carry out the integration. We can integrate each term. So first of all, how would we integrate 1/2 by itself? Right?
Just write 1/2 x because it's a constant.
1/2 times x?
T.
You say, yeah, but this is a t problem. You know, the t boils over because you've left the pot on to, no, because it's a problem written in terms of t's instead of x's, so we need to make sure we're using the same variable throughout. Yeah, integrating 1/2 is going to give us 1/2 times our variable. How about integral of 3/4 t? That?
3/8 t squared.
We're going to get 3/4 t squared divided by 2, which will indeed give us 3/8 t squared. And finally, how do we integrate 1/4 t to the negative 2?
You'd use the inverse power rule, so it'd be 4t to the negative 1, or it'd be negative 4t to negative 1.
We get 1/4 t to the negative 1 divided by negative 1, which is the same as 1 over minus 1 over 4t. And so our final answer is going to end up with 1/2 t plus 3/8 t squared minus 1 divided by 4t.
Plus c.
Indeed. Yeah, so I think this will be our final answer. Good job remembering that you always got to have that plus c when you do an integral like this. So we can't just take integral of top divided by integral of bottom, but if we have a fraction like this that we can split up into simpler fractions, that's something that can generally be done to make your life a little bit easier. Any questions or comments on that one? Alrighty, 1 over x. So for that, I'm going to rewrite this one as x to the negative 1. And if we use reverse power rule on this, we'll add 1 to our exponent, divide by the exponent, and get x to the 0 over 0 plus c, yeah? Kinsey? So it looked like you had something to say about this.
Oh no, you can't divide by 0.
Oh my gosh, I just divided by 0. That's embarrassing. So here we run into the issue where if we have x to the negative 1 power specifically, we can't actually use the reverse power rule, because if we did, we would be dividing by 0 here. N plus 1 would come out to 0 in the denominator. So what can we do instead? Can anybody think of a function that we've seen whose derivative is 1 over x? Does it?
Natural log.
Yeah, turns out natural log is an antiderivative of 1 over x. Except I'm going to add a slight twist to this. which has confounded Zach for the last couple of classes. I'm actually going to write this as the natural log of the absolute value of x, rather than just plain old natural log of x. Dr. Gerstle, why are you throwing in an absolute value sign somewhere? Hoo, ha, ha, he. We'll talk about that in the next standard. But don't worry about this one for standard 11. This is just more of a tease to introduce why can't you just use the reverse power rule on 1 over x. Turns out an absolute value sign needs to get involved in order to get the actual integral of 1 over x. Any questions or comments about any of these? All right, that's going to do it for standard 11. Moving right on along. So,
Halfway done now.
say what?
Halfway done with the standards.
Oh yeah, halfway point. It's appropriate, right before fall break. We're about at the halfway point in the semester too. So, good job in getting to the halfway point. So, what can you expect for the quiz on Wednesday? Most likely I'm going to give you a couple integrals and tell you to evaluate. So, you should be prepared for that. Alrighty, let's see. 1, 2, 1, 2, 3. Okay, so next standard is going to be pretty similar to this last one. We're just going to be talking, and honestly, this will be a pretty short standard. In this standard, we're going to be talking about how you can integrate trig functions and exponential functions, as well as get to the mystery of why is the integral of 1 over x natural log of the absolute value of x, rather than just plain old natural log of x. So to start with, if you remember back, let's see, in standard, 3 standards ago, in standard 9, we talked about how to differentiate all of these different types of functions, where we said that the derivative of sine of x is cosine of x, the derivative of cosine is negative sine, the derivative of tangent of x is secant squared of x, where secant is 1 over cosine. The derivative of cotangent of x is negative cosecant squared x, where cosecant is 1 over sine. The derivative of secant, 1 over cosine, is secant of x times tangent of x. And finally, the derivative of cosecant of x was negative cosecant of x cotangent of x. I think we did these first 3 in secant in class, and then these 2 I kind of left as an exercise to you using the top 2 formulas and the quotient rule. And we also, in standard 9, found that the derivative of an exponential function, a to the x, is going to give us a to the x times natural log of a, which, if we plugged in e for a, would tell us that the derivative of e to the x is just e to the x, using the fact that the natural log of e is just 1. And we also saw that if we were to differentiate a log function, log base a of x, we're going to get 1 divided by x times the natural log of a, which in turn implies that if we take the derivative of natural log of x, we just get back 1 over x. So these are kind of all the formulas that we found in Standard 9 when we looked at kind of a couple of weeks ago. So what I'm going to do today is talk about how can we do all of these backwards. And by doing all of these backwards, I don't mean I'm just going to not look at you for the rest of class. I mean, if these are our derivative formulas, how can we find antiderivative formulas? In other words, how do we integrate these things? So let's take a look. I'm going to start on second page now of the packet. So, with what we know about differentiating, that the derivative of sine is cosine, the derivative of cosine is negative sine, what can we say about the integral of cosine of x? In other words, what function would we have to differentiate in order to get cosine? Right, John? Yeah, so the integral of cosine of x is going to end up being sine of x plus c. Just like with the integrals we saw in the last standard, anytime we integrate, we always need to have our plus c term at the end to account for the fact that if we were to differentiate sine of x plus any constant, the derivative is going to come out to cosine of x plus 0, which is just cosine of x. How about integral of sine of x? Sam?
Negative cosine.
Negative cosine? Why negative cosine?
Because the derivative of cosine x is negative sine x. So you get throw in the extra negative.
Yeah. We need that the integral of sine is going to come out to negative cosine, since the derivative of negative cosine of x is going to give us the negative of negative sine of x, which is just plain old vanilla sine of x. Plus c. Always got to have that plus c. So, with derivatives, when we differentiate sine, we get positive sine, we get positive cosine, and the derivative of cosine gives us negative sine. A negative sign pops out when we differentiate cosine. Turns out when we're doing integrals, the opposite is true. When we integrate positive cosine, we get positive sine, but when we integrate positive sine, we actually are going to get the negative of the cosine function. How about if we were to integrate e to the x? Yeah?
Just be e to the x plus c.
So straightforward enough, I think. The derivative of e to the x is itself. So the integral of e to the x is also just going to be itself for the same reason. Except, of course, we also have to add the plus c since we're integrating. And finally, how about if we were to integrate something like 3 to the x? This one's a little bit trickier. Something like this formula might be helpful. If we were to differentiate 3 to the x, we would get 3 to the x back, but times another constant, this natural log of 3 term. So what function would we have to differentiate in order to get back 3 to the x by itself? Keeping in mind, it's probably going to involve 3 to the x somehow. Since the derivative of 3 to the x is 3 to the x times natural log of 3. Here's a hint. What constant are we going to have to multiply 3 to the x by in order for the natural log of 3 term we would get from normally differentiating 3 to the x to kind of cancel out with that constant? Anna?
1 over the natural log of 3.
Well, let's see. If we were to differentiate 3 to the x times 1 over natural log of 3, I think that would give us 3 to the x times natural log of 3 times 1 over natural log of 3. Because constant multiple rule says multiplying by a constant like 1 over natural log of 3, that just gets pulled along for the ride. I like it. Yeah, so it's going to turn out to be the case that the integral of 3 to the x is going to be 3 to the x divided by natural log of 3, and all of that then plus a constant term. Okay.
Can you go over why it's 1 over ln of 3? And or what was that rule called?
This rule, why integrating 3 to the x gives us 3 to the x over natural log of 3?
Yeah.
Well, we don't really have a name for this rule yet. Click on the next page. On the next page, I don't have a name for it. I just call it a theorem. But, Hannah, why did you say 3 to the x times 1 over natural log of 3?
1 over natural log of 3 would just be a constant, and when you take the derivative of that, then there would be the natural log of 3, and so you need it to cancel out, so then you just have regular x.
Yeah, I agree. If we were to take the derivative, Josh, of 3 to the x by itself, we would get 3 to the x times the natural log of 3 term.
Yeah.
So if we start with a 1 over natural log of 3 multiplied by 3 to the x, 1 over natural log of 3 is just a constant. So when we differentiate this just gets pulled along for the ride. And so if we differentiate that, we would get 3 to the x times natural log of 3 for the derivative of just the 3 to the x term. And then that times 1 over natural log of 3 is going to cancel out with this extra natural log of 3 term we would get to just leave us with 3 to the x. So that's why when we differentiate an exponential function, we need to multiply by natural log of a, in this case natural log of 3. It's going to turn out to be the case that the opposite is true. In order to integrate an exponential function, we actually divide by natural log of a instead, to kind of cancel out with the fact that differentiating would multiply by it. So integrating, we're going to divide by it so that they sort of, the two processes cancel out with each other. Are there questions or comments about any of these? So if we flip to the third page, I'm not going to write all these down on the board, but basically, if we were to rewrite each of these trigonometric integrals backwards, we get that the integral of cosine is sine, the integral of sine is negative cosine, integral of secant squared is tangent, integral of cosecant squared is negative cotangent, integral of secant x times tangent x is just secant x, integral of cosecant x cotangent x is going to give us cosecant of x. All plus c, of course. And that's maybe a little bit more of interest to us, is going to be this one. which says for any value a greater than 0, with a not equal to 1, it's going to turn out to be the case that the integral of a to the x will be a to the x divided by natural log of a plus constant c. So why is this? Why is it the case that if we integrated a to the x in general, we'll always get just a to the x back divided by natural log of a?
Because it's just what we did over there, except 3 is equal to a.
Yeah, it's basically the exact same reason as what we do over here, just replacing 3 with an arbitrary a. There's nothing special over there about 3. Turns out that that idea works for any constant. And so our proof, this comes down to the fact that if we were to differentiate a to the x divided by natural log of a, that's going to be the same as the derivative of 1 over natural log of a times a to the x. Keeping in mind 1 over natural log of a is always just going to be some constant value. We'll get 1 over natural log of a times the derivative of a to the x, which we said was a to the x times natural log of a. Swoosh, swoosh. This comes down to a to the x again. So the fact that the derivative of a to the x divided by natural log of a turns out to be equal to a to the x is going to tell us that the integral of a to the x has to be a to the x over natural log of a plus some constant c. Since integrals essentially are undoing the action of taking the derivative, they're just taking derivatives backwards, so to speak. The fact that the derivative of a to the x over natural log of a comes up to a to the x means the integral of the derivative should be equal to the original function plus c, of course. Any questions or comments about that? Okay, so now it's finally time to take a look at why is the integral of 1 over x natural log of the absolute value of x rather than just plain old natural log of x. That's going to be our next theorem. So let's take a look at the graph of natural log of x to help us. That spook chalk flew out of my hand. The chalk flew out of my hands while I kept a good firm grasp on the eraser. So here's a question. If you remember, here is a graph of what f of x equals natural log of x looks like. Where we have this sort of vertical asymptote here at x equals 0. And this is our natural log function starts growing really fast, but then grows more and more slowly as time goes on. So if we want to answer the question of why natural log of the absolute value of x and not just plain old natural log of x, for what values of x is natural log of x defined? In other words, what can we say about the domain of the natural log function? What values of x can we plug into natural log and get an output that makes sense? Rachel?
X is greater than 0.
Yeah, looking at the graph, we need x to be strictly positive in order for natural log of x to make sense. For similar, and we talked about why x has to be positive back in standard 9. It's because we need e to any power can never be a negative number or 0. How about 1 over x? What has to be true about 1 over x in order for, or what has to be true about x, excuse me, in order for 1 over x to be defined? Sam?
X just can't be 0.
Yeah. We mean that 1 over x is going to be defined if x is non-zero. And finally, I want to look at the natural log of the absolute value of x. Which, break out the yellow chalk here. If we were to look at natural log of absolute value of x, if x is positive, then natural log of the absolute value of x is going to be behave just like natural log of x for x greater than 0. The difference is, if we were to plug in some negative number for x, could we take, for instance, the natural log of the absolute value of -1? See it?
Yeah.
What would natural log of absolute value of -1 come out to?
Natural log of 1.
Which is?
0.
Yeah, which is just going to come out to 0. So it's going to turn out to be the case that natural log of absolute value of x can also be defined for negative numbers. And in fact, it's going to be the mirror image of plain old natural log of x, where we've taken natural log of x and reflected it across the y-axis. And so our natural log of absolute value of x is just going to look like this yellow graph here. And so with that in mind, for what values of x is natural log of absolute value of x going to be defined? Josh?
If x doesn't equal 0.
Yeah. If we need that x is not equal to 0. We still can't take natural log of 0 or absolute value of 0. No matter how you write 0, you can't take its natural log. But if x is positive, then natural log of absolute value of x is just natural log of x, so it's defined. If x is negative, then absolute value of x will be positive, so we can take its natural log. And so turns out that natural log of absolute value of x is natural log of absolute value of x is going to be defined. I wrote this down with a lisp. If going to be defined, it's going to be defined as long as x is non-zero. Now, what observations do you notice about where these three functions are defined? Specifically, 1 over x is defined for any non-zero x. Out of natural log of x and natural log of absolute value of x, Paul, which of these two functions is going to be defined over the same values of x as 1 over x?
Just again.
Sure. 1 over x is going to be defined anywhere that x is not equal to 0. Out of these other two functions that we looked at, which of these is also going to be defined over the same values of x?
Natural log of absolute value of x.
Yeah, it's going to turn out to be this one. And so, Zach, to kind of answer your question, to answer the question you asked last class of why isn't the integral of 1 over x just natural log of x? It's because natural log of x is only defined for positive numbers, whereas natural log of the absolute value is defined everywhere that 1 over x is defined, specifically all non-zero values of x. So in other words, we want any antiderivative of 1 over x to be defined over the same values of x as 1 over x. In other words, for all x not equal to 0. And natural log of x doesn't fit the bill. Natural log of x isn't defined for all non-zero numbers, it's only defined for positive numbers. But natural log of absolute value of x is going to be defined at more points than that. It's going to be defined at all non-zero x, just like plain old 1 over x. So we'll say natural log of absolute value of x does this, but natural log of x does not. Any questions or comments? I've got a question, Dr. Burstall. Why is it that the derivative of natural log of the absolute value gives us the same thing? Gives us 1 over x? That's a good question, puppet Dr. Burstall. So let's also ask the question of why is the derivative of natural log of absolute value of x equal 1 over x? It's all fine and dandy if these two expressions, 1 over x and natural log of absolute value of x, are defined for the same values of x. But if the derivative of natural log of absolute value isn't equal to 1 over x, it still wouldn't work as an antiderivative. Natural log of absolute value wouldn't be an antiderivative of 1 over x. So we need to actually check that the derivative of natural log of absolute value is 1 over x. And so, in order to show this, I want to actually look at two separate cases. One where x is positive, and one where x turns out to be negative. So if x is positive, what can we say about absolute value of x? In other words, if x is a positive number, what relationship does absolute value of x have to plain old x? Sam?
They're the same thing.
Yeah, they're the exact same. As we've seen, if x is positive, then the absolute value of a positive number is just that number again. So if x is positive, the derivative of natural log of absolute value of x is just going to behave the same as the derivative of natural log of x, which, as we've seen, is just going to give us 1 over x. So if x is positive, the derivative of natural log of absolute value will behave just like the derivative of natural log of x. How about if x is negative? Specifically, if x is negative, relationship does the absolute value of x have to plain old x? Rachel?
Well, negative.
Yeah. If x is negative, here we're using our definition, our piecewise function definition, where the absolute value of x is x if x is greater than or equal to 0, and negative x if x is less than 0. If x is a negative number, then the derivative, then natural log of the absolute value of x is just going to be equal to the natural log of negative x. Or here we could just replace absolute value of x with negative x. How can we differentiate natural log of negative x? Standard 9 type question. Sam? Okay. We have I like it. We can use the chain rule. We have two functions going on where we have an inner function, h of x is negative x, and an outer function. What would we get if we used the chain rule on natural log of negative x here? Right, want to give it a go?
1 over negative x times negative 1.
Yeah, we'll take 1 over negative x. That's our g prime of h of x. G prime of x is 1 over x. H prime of x is negative 1 here. So our g prime of h of x is 1 over negative x. So 1 over, well, what I just said, 1 over negative x. Times the derivative of our inside function, h prime, which is going to give us negative 1. And so we'll get 1 over negative x times a negative 1 term. And lo and behold, it just simplifies down to 1 over x. And that is why the derivative of natural log of absolute value of x gives us 1 over x. It comes down to the fact that if x is positive, natural log of absolute value has a derivative of 1 over x. And if x is negative, the derivative turns out to be the same thing. It just takes an extra step to get there, but it comes out to 1 over x in the end of the same thing. Any questions or comments about natural log of absolute value of x and why we get this integral? What else we got? Okay. All right, go ahead and take the next few minutes, and if you look at the next page, I've got a few sample integrals for you to evaluate involving some trig and exponential functions and potentially logarithms showing up. So what I'd like for you to do is to take the next few minutes, and as always, you're welcome to work with the people sitting around you and see what you can make of the 4 integrals on the next page of the packet. For some of these, you'll have to use a combination of things we talked about in this packet and things we looked at in the last packet as well. as always, if you're feeling stuck on something, feel free, you're encouraged to talk to your neighbors and or ask me. I like it better now. If you feel like you have answers, turn to your neighbor and see if they agree with what you have so far.
I'm trying to figure it out right now. If I wanted to cosine x, minus cosine x, easy derivative of that is.
So I'm going to come back together briefly as a class to talk about this last question.
I think you're right.
I'm looking around, it sounds like this one's causing a few issues. So I think I know how to integrate minus 2 over 5x. How are we going to integrate sine squared x plus cosine squared x? Kenzie?
Sine squared x plus cosine squared of x equals 1. So I just did 1 minus 2 over 5x.
Oh, Dad Zooks. We know something about that expression. That's always 1 because sine and cosine of x are always x and y coordinates of points on the unit circle. So that's going to tell us that Dr. Garcel's trying to pull a fast one on you. And really, this is actually the function I asked you to integrate. And so if we want to integrate 1 minus 2/5 x to the negative 1, how are we going to integrate that? Ellen, want to give it a try?
Yeah, so you'd have x, and you'd use the power rule, so you'd have x plus x to the negative 2 over 5.
X to the negative 2. So you're subtracting 1 from the exponent? And say, I think if we were differentiating that, we would end up with something times x to the negative 2, but not if we're integrating necessarily.
Would be ln, negative 2/5 ln.
Yeah, I think we're gonna have negative 2/5 ln
ln x. ln the absolute value of x.
So we get x minus 2/5 natural log absolute value of x. This is the first. We actually finished 2 standards in one class. Y'all want a double quiz on Wednesday?
Yes.
Yeah.
Yeah, it's worth it. Let's do it.
All right, let's put it to a vote. If I gave you a double quiz, you'd have like twice the time. I'd give you like 20 minutes to work on it. It would be 2 pages. You could have masteries on each separately. So all those who would like a double quiz on Wednesday.
I can't hear you.
1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, that's a majority. Okay, so on Wednesday we'll have a standard 11 and standard 12 quiz, and then jump into standard 13 and start looking at motion problems.
Dr. Ursula,
Tomorrow at 1? Yes, I do. You got it. See you tomorrow.
Can I come in at 2 with finance, please?
Yeah.
For
Yeah,
text send.
yeah, no problem.
She's gonna do flat.
Thank you, Dr. Gerstle.
Take care, Riley. Have a good one.
You too.
In class.